Yes, maybe we can start.
All right, let me just share. Am I audible? Is it
Yes,
all right? Because I am not using the headphones, so I'm not sure whether. Okay, let me just share the screen now.
yes.
Can you
Welcome.
see the screen?
Yeah, welcome everybody to the second talk of the day. We have Arghyajit Datta from South Korea, and he's going to talk about revisiting matter-antimatter asymmetry in an era of early matter domination. Maybe I'll send you a reminder when 5 minutes are left.
Sure, sure. Okay, so thanks, Sonish, for this nice introduction and also for inviting me to speak in this nice, very popular seminar series. As already mentioned, I am Arghyajit. I am currently a postdoc at Chung-Ang University, South Korea. And today I will talk about early matter domination and its effect on matter-antimatter asymmetry. The talk mainly will be based on these 4 articles, which I wrote in collaboration with these people. And more specifically, I will focus on these 2 articles because of the time constraint. Okay, so let's start with a statement that, so let's start with a statement that we live in a universe where there is more matter than antimatter. How do we know that? People have searched for antimatter structures within our solar system to the furthest distance where our experiment can probe, and we have not found any antimatter structures. There are 2 ways one can search for antimatter structures. One is you can directly search them in a cosmic rays. Experiment like Pamela or AMS, or more recently AMS2, they are more suitable for these searches, and they have not found any anti-nuclei or any antimatter structures apart from those which can be generated because of the collision between matters within the cosmic rays. The other way of searching is you can search them indirectly by looking at the photon flashes generated because of the interaction between matter and antimatter. And experiment like Egret or Comtel, they search for these diffuse photon flasks. And again, non-observation of these photon flask give a bound on the antimatter fraction, which is, for example, of the order of 10⁻⁶. And also, you can independently give a bound on the radius of the matter-dominated universe, which is like of the order of 1 gigaparsec, which is also similar to the visible radius of our visible universe. So all these astrophysical observations actually tells us that there is no antimatter structure present in our visible universe. Knowing this, cosmological observation also give a strong bound on this matter-antimatter asymmetry parameter. Of course, when I am talking about matter-antimatter asymmetry, I am talking about baryonic asymmetry. So it's generally defined like this way. So you take the ratio between difference between number density of baryon and antibaryon, and of course in the denominator we have number density of photon. So this plot actually shows how you can constrain this number. So most stringent bound comes from CMB observation, which this blue patch in this graph, and it tells that eta b has to be of the order of 10 to the minus 10. So now, from a theoretical perspective, the main goal or the main issue is that to generate such asymmetry dynamically. There are various possibilities, but my favorite one is this leptogenesis via baryogenesis mechanism, because not only it can explain the baryon asymmetry of the universe, but it can also naturally generate the neutrino mass. Well, if you look at the simplest Typhon seesaw version of it, what we generally do is that we generally add 3 right-handed neutrino on top of standard model particles, and then you write the most general Lagrangian, which is allowed by the standard model gauge symmetry. Then after the spontaneous symmetry breaking of electric symmetry, you can construct a mass matrix for neutrinos. For 3 right-handed neutrinos, these are 6 cross 6 matrix. You diagonalize this matrix, you generally get the light neutrino mass. Most interestingly, in this case, the neutrinos becomes a Majorana type, so they are their own antiparticle as well. Now, on the other hand, the same Lagrangian also contains all the ingredients which actually requires to generate baryon asymmetry. So this is a Yokowo interaction. It can source the CP violation because it is a complex matrix. This is a Majorana mass term, so it is a lepton number violating term, so it can source the lepton number violation. And with these two conditions satisfied, you can have a out of equilibrium condition satisfied when right-handed neutrino decays out of equilibrium. So since all the conditions are satisfied in this case, you can generate a finite amount of lepton asymmetry, which then sphelerons above, when the sphelerons remain in equilibrium, they can convert that asymmetry to baryon asymmetry. So in this way, in this minimal setup, you can generate baryon asymmetry as well as neutrino asymmetry. Well, let's go a little bit deeper because I will mainly focus on this setup. So in this setup, the CP asymmetry is generated because of the interference between tree level decay and loop level decay of right-handed neutrinos. And then what people generally do is that, knowing this CP asymmetry, they solve the Boltzmann equation for right-handed neutrinos and B minus L yield. In general, there should be 3 equations for right-handed neutrinos and 1 equation for B minus L, but the life becomes simpler if you take a hierarchical mass limit for right-handed neutrinos. So in that case, lightest right-handed neutrino will contribute to the lepton asymmetry, and then you only need to solve these 2 equations to get the final B minus L. And then from that final B minus L, using this relation, one generally calculate the final baryon asymmetry. So in most of the articles, you generally see this prescription used to get a finite amount of baryon asymmetry. But the story does not end here. Please note that there is also charge lepton-Yokowo interaction, which is present within standard model. This interaction also play a vital role in leptogenesis. How? So when when we are in a very high, in the early universe, the asymmetry generated from right-handed neutrino decay and inverse decay, the lepton asymmetry generated in all lepton flavors are generally indistinguishable. But as the temperature decreases, what happens is that in between decay and inverse decay, charge lepton-Yokowo interaction can occur. So for example, below 10 to the 5 into 10 to the 11 GeV, tau Yokowo interaction come into equilibrium. So the asymmetry along tau direction become different compared to muon and electron direction. So in this regime, you cannot simply use this prescription, which I told earlier. So in this situation, what one needs to do is one need to construct if you simply calculate, if you want your life simpler, you need to construct a quantum coherent basis LA, which is a linear combination of LE and L mu, and you have to evolve asymmetry along tau direction and A direction independently, following this type of Boltzmann equation. Similarly, as temperature decreases, let's say around below 10 to the power 9 GeV, muon-Yokowo interaction also come into equilibrium. And then again, this 2 flavor prescription breaks down because there is no quantum coherence in LA. In that case, you have to evolve the Boltzmann equation for E, mu, and tau direction. So then finally, to get the final B minus L, you have to add all these independent asymmetry along this independent lepton direction. How much does it affect? So this plot shows how does it affect. Let's take a right-handed neutrino mass of the order of 10 to the 10 GeV. In this case, following this prescription, we see that if you want to exactly calculate the lepton asymmetry, you should work in 2 flavor regime. But let's say that you want to work in 1 flavor regime, and let's say if you want to compare the 1 flavor and 2 flavor. So here you see that how they differ. So this black line shows the evolution of asymmetry for if you take into account 1 flavor regime. And the red line shows the evolution of asymmetry in two flavor regime. And from these, you can easily see.
Can I ask a question?
Yeah, please.
Is there any reason behind choosing M1 to be turned to a 10 GeV, 500 mass?
No, the reason is, for this case, I just wanted to show that if right-handed neutron mass is 10 to the power 10 GeV, what is the effect of these two flavor or one flavor prescription? If you have, that's I just wanted to show in this plot. The reason is, if you take 10 to the power 10 GeV.
So it is kind of for an example, right?
Yes, for an example.
So what happens if you choose some other M1? I mean,
yeah,
it is the same asymmetry thing.
I will show.
Okay. Thank you.
Yeah. So from these, we are seeing that, of course, if you want to accurately calculate the symmetry, you should follow these flavor prescription, which I showed earlier. So this is a standard pictures, so which is called flavor leptogenesis. But all the discussion till now, which I was having, was based on one assumption that everything was happening in a radiation-dominated phase. But although this assumption is like a valid assumption, but I mean, it may not be correct assumption, because what we know from experiment that our universe should be radiation dominated during BBN period, that is around 1 MeV. We do not know what was the state of our universe above 1 MeV. We just extrapolated our previous assumption that it can be a radiation dominated phase. On the other hand, matter domination can can be general. It can appear naturally in early universe above BBN. For example, we can have a oscillating inflaton field after inflation, and it can dominate temporarily. Or you can have a very large heavy particle originated from a very higher symmetry group like GAT, whose decay rate is very small, so it can dominate temporarily. Or in an exotic sense, we can have PBH primordial black holes or cosmic strings, or like any type of cosmological defects. They can also dominate in the early universe temporarily. So all these situations can lead to an early matter domination. So if now what we will ask is that if this type of early matter domination prevails in the early universe, and if leptogenesis framework, which I was discussing earlier, is active during this early matter domination, what impacts the matter domination has? That is our question. Now, prior to our work, the previous works, whenever we talk about early matter domination and its impact on baryogenesis via leptogenesis, people generally talk about these things like there is the effect of modified expansion rate, or like the entropy injection into the system, or like the effect of non-thermal particle production. However, all of these works misses these things, that because of the early matter domination, the equilibration temperature of different standard model interactions also changes. And these can also affect the leptogenesis process. That is what we showed in that work. So let us take one example of post-inflationary heating phase. Let's take an inflaton phi, which somehow has this type of T attractor potential. So the potential has very unique feature. It has a very flat potential for a larger phi value, and it has some well type structure for small phi value. So during the flat period, it can inflate the universe, and during this oscillation well region, it can start oscillating, and it can distribute its energy to the standard model particles to create that standard model bath. So and if this transfer of energy process is small, actually you can have a matter domination. Let's see how. So let's take an effective coupling of the order of 10 to the minus 6 with standard model particles and the inflaton field. And if we have this type of coupling, so this plot actually shows how the energy density of the inflaton varies with respect to scale factor of the universe, where A equals to 1 indicates the end of inflation. So as you can see, initially, just after the end of inflation, we can have a matter-dominated period. Then when this inflaton all transfer its whole energy, we can get the radiation-dominated phase. So also another important thing is that during this matter-dominated period, the temperature falls differently compared to the standard radiation-dominated phase. So in this case, we can have a large maximum temperature, and then it falls, differently compared to the radiation phase. And after, when the radiation starts to dominate, it falls as scale factor to the power -1. So from this, we are seeing that we can have a finite amount of matter-dominated period for this type of effective coupling. And also, with this effective coupling, you can also tune how long these matter-dominated last. For example, this plot actually shows that. So in the y-axis, we have plotted Tmax by T reheating. This is Tmax and this is T reheating. And we just, in x-axis, we have just increased the effective coupling. So we can see for different type of potential, so k equals n equals to 2 or n equals to 4, n is this one, sorry. So this is n, the power of potential. The difference between Tmax and T reheating reduces as we increase the coupling. So that means our matter-dominated period also gets shorter for larger effective coupling. So in this setup, we can, so this thing says that we can generate a finite matter-dominated period. Now see, what would be the impact on this matter-dominated period on the equilibration temperature of the different interaction. For example, let's take the interaction, the equilibration temperature for Charles-Lepton-Yoko interactions. To get the equilibration temperature, the simplest way is you can calculate the interaction rate and then compare it with the Hubble. So this plot actually shows that. So in the y-axis, the gamma by H is plotted, and in the x-axis, the temperature was plotted. The solid lines indicate the gamma by H variation for calculated in standard radiation-dominated phase. And this dotted line shows the variation of gamma by H when there is a matter domination. Yeah, please.
May I ask a question?
Yeah, please.
So in the temperature plot, during the matter-dominated phase, the temperature should drop more sharply, right? I mean, more quickly than radiation-dominated.
No. If you look this one, so look at this phase. So it falls less sharply compared to radiation-dominated phase.
But during the matter-dominated, the temperature should fall more quickly, right?
No. It should be T to the power minus A to the power minus. If you want to calculate in terms of scale factor, it should be minus, for n equals to 2. I think it should be minus 3 A to the power minus 3 by 8, which is smaller than A to the power minus 1. Yeah. So it should not be faster. It should be smaller.
Okay, but I mean this matter-dominated is pressureless, right?
Yes.
So
but
for pressureless
depends
dust,
on which potential you are taking. Yeah, but go on.
Yeah, for pressureless dust, the temperature should fall 1 by A square.
1 by how?
A square.
I don't think it should be A to the power minus 3 by 8, something like that. Not A square.
No.
Are you?
Because the temperature goes by the 1 by lambda square, where lambda is the de Broglie wavelength, and that's why temperature should fall 1 by A square.
I think you are not.
We can discuss it, no problem.
Yeah, of course.
You may go
but
on.
I don't think it will fall in this case as A to the power minus 2. No, it's not. Okay, maybe I will talk with you later, but I have checked.
No, may I comment? Because in the matter domination, in the radiation domination phase, this temperature is solely controlled by this energy density of the radiation. And radiation energy is proportional to pressure in the radiation domination phase. So
Yes.
rho is proportional to pressure, and then and rho and P both proportional to T to the power 4. And then
So
P
that's
goes
why,
as 1 over A
yeah.
square in the reduction domination phase. But in the matter domination phase, as you correctly pointed out, it falls as 1 over A to the power 3 by 8. It is much slower than A to the power 8. Because this in the matter domination phase, this energy density does not solely controlled by this energy density of the radiation.
Yes, it's controlled by the
That is
energy
why T to
density
the
of fire.
that is why T is proportional to E to the power 3 by 8, as you correctly pointed out.
Yes,
Yeah.
yes. Thanks. Yeah, I mean, if you have still doubt, I can talk with you. Maybe
Yeah.
I just
Sure.
move on. Yeah, so what I'm trying to say is that because of this matter domination, we are seeing for this plot, we are just seeing that there is a shift in the equilibration temperature for tau and Yoko interaction. So you see with this amount of coupling, we are seeing that the tau Yoko interaction come into equilibrium quite late compared to the standard radiation dominated case. As a result, this was the earlier picture for flavor regimes. Now with this amount of coupling 10 to the minus 6, our equilibration temperature goes down. For tau Yoko equilibration temperature goes down to 10 to 7, I mean almost 8 into 10 to the 10 GeV. Now let's take a mass of right-handed neutrino of the order of 10 to the 11 GeV. So now in this case, you do not need to work into flavor prescription, because since tau is not in equilibrium, you can construct a one quantum coherent state L1, and you can solve the Boltzmann equation for the lepton asymmetry generated along L1. How does it impact? So this plot actually shows how the parameters impact. In the y-axis, I have here plotted YB final baryon asymmetry. In the x-axis, I have plotted imaginary part of theta. I have not mentioned about it, but think of it as the parameter which control this Yoko coupling. So larger imaginary part of theta will increase the Yoko coupling of neutrino. The magenta point shows the variation of YB generated in standard radiation dominated case, and these blue points indicates the variation of YB in this matter dominated case, plus the shift of flavor has been taken into account. And from there, here in this plot, you can clearly see that you get a less allowed parameter point compared to standard radiation dominated case. Of course, this is for one coupling. Now, if you can do many things, like you can vary this coupling and see how does it affect for whole parameter allowed parameter space for leptogenesis. So in the x-axis, I have plotted again the effective coupling. In the y-axis, I have varied the temperature, and in the right axis, I have plotted the scale of the leptogenesis. As I discussed earlier, with increasing effective coupling, we see that the maximum temperature and heating temperature also increases. Not only that, we are also seeing the tau Yoko equilibration temperature also increases. And muon Yoko equilibration temperature increases for some time, then when it reaches the standard radiation dominated value, it becomes constant. We want to we want to stay within the matter dominated phase. So this yellow region is our region of interest.
Can I ask a question?
Yeah, please.
Yeah. In the right panel, like right axis, you have plotted M1, which is the mass of the right neutrino, as you pointed earlier. So, I mean, why this is the range? I mean, do you have any comment on that? Why this is the range, like 10 to the 7 to the 30? Why not other values?
Like what? I mean, which value do you want? I mean, can you?
No, I don't. I mean, I mean, just asking a question that why this is the range.
The reason is, so I have not mentioned many things, like in thermal leptogenesis prescription, there is a bound called Davidson-Ibarra bound, which tells that if you have what is the minimum value of right-handed neutrino mass which can generate the correct baryon asymmetry, and that value is 10 to the 9 GeV. Okay.
Oh, that answers that. Okay, fine.
Yeah. So now what I wanted to see is that in matter dominated phase, whether that bound stays or not, or whether there any modification on that bound. or whether there is any modification in the parameter space. That's what was our goal. That's why I just varied in this mass regime.
Yeah, I got it. Please go ahead. I got it.
Yeah. So, and also this is, please note that this is for, of course, for hierarchical right-handed neutrinos. For degenerate neutrinos, this is different. It can be as low as, I think, TeV range.
Okay. Thank you.
Yeah. So here you can see these light brown patches. This light brown patch tells the allowed parameter space when this shift of flavor effect has not been taken into account. On the other hand, these dark brown patches shows the allowed parameter space when this shift of flavor regimes has been taken into account. And from this, you can clearly see that you are getting less allowed parameter space compared to the traditional calculation what people generally do. So this is the summary of the first part. So what I wanted to show in the first part is that early matter domination can affect this equilibration temperature of standard model interaction, and it can shift the standard flavored prescription flavor regime of leptogenesis. And if you want to calculate the lepton asymmetry, you should not blindly follow the standard pictures, because you are maybe calculating you are maybe calculating or overproducing your asymmetry. So that's one check one should keep in mind. Now, in the second part, I will talk about asymmetry in leptonic sector. So previously I was talking about asymmetry in baryonic sector, which we found out to be 10 to the minus 10 order. The question is, what is the value of leptonic asymmetry? So if you want to evaluate it intuitively, so we have a positive 10 to the power minus 10 order of baryon asymmetry. That means we should have more baryon than antibaryon. That means we should have more proton than antiproton. And from charge neutrality, this tells us that there should be more electron than positron. But it does not tell what should be the asymmetry between neutrino and antineutrino. In general, intuition is like it should be of the order of minus 10, but it's just an intuition. Experimentally, also we can get some intuition about this neutrino asymmetry from the detection of helium-4 abundance, from which is generated during BBN. And so during BBN, the helium-4 abundance mainly depends on the neutron by proton ratio at the time of freeze out of these interaction in NP conversion processes. So if you have a less number of N by P, that means you will get a less number of helium-4. And the number of N by P can be fixed if you have a neutrino asymmetry or electron neutrino asymmetry, that will reduce this N by P ratio, and that can reduce the YP observed value. Now, prior to 2026, Empress actually found a very small value of YP compared to the standard BBN value. And you can do statistical fitting, and you can show that for this amount of YP, there can be a asymmetry, neutrino asymmetry, and you should have a electron neutrino asymmetry, which is of the order of 10 to the minus 3, and which is also a positive number. So now, if this is true, then from again theoretical perspective, we should try to find a way to generate such large electron neutrino asymmetry, which is of the order of 10 to the minus 3. Again, leptogenesis can be a good candidate because it's actually generate the lepton asymmetry first. But if you stick to the thermal prescription, there is a problem, because in thermal leptogenesis framework, leptogenesis occur at energy scale or temperature around the mass of the right-handed neutrino. So If the mass of the right-handed neutrino is higher than the speleron decoupling temperature, it can generate a lepton asymmetry, but that asymmetry gets converted to baryon asymmetry. So this window is forbidden for generating a lepton asymmetry or neutrino asymmetry. So this is the window which is which remains safe for generating lepton asymmetry in this way. But then also there is a problem. So in this regime, if you believe in thermal case, your right-handed neutrino mass has to be smaller than 132 GeV. But then Higgs mass can prevent the right-handed neutrino decay. So you may not get the you may not generate the neutrino asymmetry in this region even if you stick to the thermal case. So knowing this, what we ask is that can early matter dominated phase help us in this type of situation? So what we did, let's take again an intuitive picture. So let's start with a scalar field phi, which has this type of potential. We added a constant energy term V0. It interacts with the thermal bath, so it can have some thermal correction to phi squared term. So if you have this type of potential in the early universe, when temperature is very high, this term can dominate compared to the m phi squared term, and your potential can look like this, where phi equals to 0 can be the minimum, true minimum of the potential. Now, since it is a true minimum, phi can stay in this phi equals to 0 position, and then its energy is nothing but V0, this distance. So this will be the flowchart in the early universe. Maybe this V0 is smaller than the energy density of radiation. So we can have standard radiation dominated phase. But as the temperature decreases, we can find a situation when ρr becomes smaller than V0. But phi can also, in that period also, phi can stick to this position. So in this case, energy of the universe will be dominated by this V0, and it can, since it is a constant number, so it can inflate the universe again. So since it is controlled by this temperature, so we are calling it thermal inflation. It does not prevail for a long time because temperature is decreasing. So we can find again a situation when Ct square becomes smaller than m phi square, then the true minima of the potential shifts to another phi equals to non-zero value, and then this phi, this field can rolls to this minima and oscillate around this minima and transfer its energy to the standard model particle and reheat the universe again. So during this oscillation, again, you can have a early matter dominated phase. So now let's look at these early matter dominated phase and zoom in. So in this period, let's couple this phi to nc bar n, our right-handed neutrino. So it has two advantages. One is during its oscillation around this minima, it can give mass to right-handed neutrino, and also it can decay to right-handed neutrino to produce the radiation bath and reheat. And on top of it, if your reheating temperature falls below that speleron decoupling temperature, and if you can have this condition satisfied that your mass of the right-handed neutrino is larger than reheating temperature or larger than speleron decoupling temperature.
Can I make a comment right now? Hello.
Yeah, please.
Can I make a comment? That you have put some condition, this m phi square greater than Ct square, but reheating phase, isn't it like reheating phase is always dominated by matter, because influence energy in the reheating phase is always greater than whatever energy is kind of transferred to other particles. So reheating phase is kind of the phase that it is always dominated by matter, is the case?
Yes.
Does it need any condition that, like, as you propose, like m phi square?
Yeah, so this one is needed. This condition, are you talking about this condition?
Not particularly this condition. I mean, reheating phase. Reheating phase.
This is a different type
reheating phase to be
of
matter.
reheating which I am talking about.
Exactly, that's fine. But reheating phase to be matter dominated. Does it need any condition? Any condition? Forget about this particular condition. Does it need any kind of condition such that reheating phase needs to be matter dominated? Because reheating phase means like rho phi has to greater than any other particle, energy index of any other particle.
Yes.
That's what I'm saying. Does it need any particular condition?
No, it does not need, but the condition is coming because it's appearing naturally because of this potential. That is what I am trying to say. So you have to find
No, maybe this particular condition is one of the case that follows that reheating phase is matter dominated. That follows it. Because reheating phase does not violate this matter domination condition. That's what I'm saying.
Yeah, you are correct.
This particular condition, maybe one of that case, whatever you are saying, maybe that follows that condition that it has to be early matter domination, but it does not need any particular condition to be followed to be matter dominated era. That's what I'm saying.
Yeah, of course. But what I am trying to say here is that I want a matter dominated period after the end of this reheating, after the end of this thermal inflation period. I just wanted to show at which condition this thermal inflation will end, and at which condition this matter or reheating period will end.
No, that's perfectly fine. But the thing is that it should not depend on any condition that it has to be matter dominated. Reheating phase to be matter dominated. That's what I'm saying. Is it true?
Yeah, of course. Here it should be matter dominated because in any places it should be matter dominated, but I just wanted to show how this matter domination appear in this type of framework.
Yeah,
that is what I was trying to say.
Yeah. But this is not the condition. So this is not the condition that which makes in a reheating phase to be matter dominated, right?
No. This condition tells us when the matter domination starts or reheating domination. Reheating starts.
Yeah. Fine.
Okay. So maybe if as I was mentioning, if the Sphellerian decoupling temperature is larger than this reheating temperature, and if because we have to produce very large 10 to the minus 3 order of asymmetry, so if you somehow resonantly enhance the CP asymmetry, we can produce large lepton asymmetry at T reheating. Although this intuition is quite simple, but constructing an exact BSM model.
5 minutes left.
Yeah, of course. I will not take lots. Yeah, it will not take more than 5 minutes. Okay, so it will not be that trivial to construct a BSM model to implement this intuition. Why? Because to have a thermal inflation, your this vacuum energy has to be very larger than the rho r, and that means your wave of the phi field has to be very large than m phi. So that means your potential has to be very flat. And the previous description which I was talking about, like this, that means the lambda phi has to be very small. It should be very, very less than 1. So that is very unstable because quantum correction can erase this type of smallness. So maybe there are other options, but we choose supersymmetric extension because in supersymmetry, this type of flat potential is natural. You can have a natural stabilization of the potential. You can have very large wave compared to the mass. So this is our particle physics setup. So we have supersymmetric E1 B-L extension of MSSM. So here where we add two superfield phi 1 and phi 2 on top of right-handed neutrinos. So along the phi 1 equals to phi 2 direction, the potential is the potential is flat, And on top of this D potential, flat potential, this stabilization term and this mu term, and also there is A and B term, those actually gives feature like this minima, which is also very far away from the origin at 0 temperature. And at high temperature, you can have this CT square, which tilt the potential a little bit up. So you can have stable, true minima at phi equals to 0. Okay, with this setup, I'm not going into the detail. You can calculate the neutrino asymmetry at reheating temperature, which depends on the number density of right-handed neutrino and CP asymmetry. And interestingly, you can also generate the small baryon asymmetry, because all phi will not decay at reheating temperature. Some of the phi can decay around T spheroid, and those right-handed neutrino produced from phi can instantly decay and produce the baryon asymmetry. Here, another interesting thing which should be noted, that in this way, if you want to produce positive baryon asymmetry, that means you should have a positive B minus L asymmetry. That means your sum of neutrino asymmetry has to be negative. But what we observed in the experiment was the neutrino asymmetry is, electron-neutrino asymmetry is positive. So you have to have a very fine-tuned situation where lepton asymmetry produced in electron direction has to be positive and other two asymmetry direction should be negative. And so as a whole, the total lepton asymmetry becomes negative. So this is the plot which shows whether we have any allowed parameter space or not. So in this plot, in the right plot, I have plotted in the x-axis the wave of this phi. So it varies from 10⁻⁹ to 10⁻¹2, and the mass of the phi is around 300 to 800. This green contour shows the y nu neutrino asymmetry of the order of 10⁻⁴. This region is less than 10⁻⁴, and this region is larger than 10⁻⁴. This red region shows reheating temperature larger than spheroid decoupling temperature. So in this region, you cannot produce lepton asymmetry. This black shaded region indicates the region where inverse decay of right-handed neutrino is larger than the Hubble expansion rate at T spheroid. So it can dilute the baryon asymmetry. So in this region also, you cannot generate baryon asymmetry. The correct baryon asymmetry, it satisfies this line, every point on this line. So you can say that every point on this blue line can generate both baryon asymmetry and neutrino asymmetry. Left plot, I showed how with larger Yokowo, with changing Yokowo coupling, how the things varies. And since we are changing very small amount, the Yokowo coupling very small amount, and we had a very fine-tuned situation, only baryon asymmetry actually varies. All the other things remain intact. So that's the thing, that we have allowed parameter space, which can explain both neutrino asymmetry and baryon asymmetry. Okay, so that's all. So what I tried to say was early matter domination can influence matter-antimatter asymmetry, be it baryonic asymmetry or leptonic asymmetry. In the first part, I showed early matter domination can change the equilibration temperature of charge-lepton-Yokowo interaction. That requires, that shifts the so-called flavor regimes, and you should be more careful if you want to calculate lepton asymmetry using this flavor calculation. In the second part, I showed that early matter domination after thermal inflation can help us also generate large neutrino asymmetry, which was indicated by Impress. And it can also generate correct amount of baryon asymmetry. Now, before concluding, I just want to add one footnote that after in January 2026, LBT collaboration actually recently evaluated a very precise value of YP by observing helium-4 galaxies. And what they found was the YP value is coinciding with standard lambda CDM. So that means there should not be any neutrino asymmetry according to this collaboration. And on the other hand, this Empress is saying that there should be very large neutrino asymmetry. So there is a possible tension between these two observational results, and I would be looking forward to see what in the future how this Empress experiment tells us about their result. So with that, let me conclude. Thanks for listening.